In the final years of the Cold War, deep inside the tank testing ranges of Kubinka, a classified report began circulating among senior Soviet armor engineers, one that made no sense to them. It described an American M1 Abrams that had allegedly survived multiple direct impacts from modern 125mm kinetic penetrators, the same long-rod darts fired from their most advanced frontline tank, the T-80U. To the Soviet engineers reviewing the numbers, the claim bordered on impossible. For more than a decade, they had trusted the physics of their own weapons, the penetration tables of the 3BM-42 Mango, and the projected defeat margins of NATO armor. And according to every calculation they had, no Western tank should have walked away from such hits. Yet the Combat Materials Directorate was now looking at photographs, grainy, declassified only by accident, showing an Abrams with deep, violent craters in its armor but an intact turret, intact crew compartment, and a functioning power pack. The external damage was unmistakable. The tank had been struck. But so too was the undeniable fact that the crew had survived. For Soviet engineers trained to think in terms of shaped charge jets, steel penetration values, and predictable armor responses, the American tank represented an anomaly that threatened the mathematical foundations of their gunnery models. For decades, Soviet armor doctrine relied on one underlying assumption. If a 125mm smoothbore firing modern APF SDS rounds hit any opposing tank at standard combat ranges, the result would be decisive destruction. It was the same logic that guided T-64, T-72, and later T-80 development: hit fast, hit hard, overwhelm at scale. The idea that an American tank could not only withstand these hits but continue fighting contradicted everything they believed about lethality and armor science. What the Soviets didn't yet grasp was that the M1 Abrams was not simply an evolution of NATO tank design. It was the product of a fundamentally different philosophy, one that rewrote the hierarchy of survivability. And as more reports emerged from test ranges, intelligence intercepts, and later, combat in the Middle East, the uncomfortable truth became harder to ignore. The Americans had created a tank that was not supposed to exist, a vehicle that appeared to violate the very equations Soviet engineers had relied upon. And that realization would force them to re-examine not only their assumptions about armor, but the T-80 itself, a tank they once believed represented the pinnacle of Soviet engineering. The deeper Soviet analysts dug into the Abrams issue, the more troubling the pattern became. Their initial instinct was to blame faulty reporting or range conditions. Perhaps the American tests were staged. Perhaps the rounds were older variants. Perhaps velocity decay had softened the impacts. But each of these explanations collapsed once they reviewed classified foreign material exploitation notes coming from Warsaw Pact partners. Eastern Bloc intelligence teams that had observed U.S. training exercises in Germany repeatedly noted a strange phenomenon. Abrams crews displayed an almost casual confidence in situations where older NATO tanks would have been far more cautious. The Soviets assumed it was bravado. It was not. Privately, Soviet engineers had long respected the T-80's firepower. Its 125mm 2A46M, one-gun firing long-rod penetrators could generate muzzle velocities exceeding 1,700 meters per second. On paper, rounds like the 3BM-42 should have penetrated any NATO frontal arc at standard battlefield ranges. Yet American armor wasn't behaving according to those tables. Something was fundamentally off. Reports suggested that the Abrams did not rely on steel layering or spaced armor alone. There were references to special arrays, classified composites, and non-metallic inserts that reacted to impacts in unconventional ways. But without a recovered sample, the Soviets could only theorize. Behind closed doors, expert panels convened at the Malyshev factory in Omstrandsmash were forced to confront a possibility they had long dismissed: that NATO had made a revolutionary leap in armor science. The term that appeared most often in Western technical literature was CHOBM, but its true structure remained unknown. What the Soviets did know, however, was that whenever the Americans spoke about it, their descriptions were deliberately vague: layers, ceramics, elastic materials, and energy-dispersing composites. None of it matched anything in Soviet production lines. More alarming was the fact that American test results didn't just show the Abrams surviving impacts. It showed the crew remaining combat effective afterward. In Soviet design philosophy, if a tank survived but the crew was concussed or immobilized, the outcome was still considered a mission kill. The Abrams appeared to defy even that standard. And as these findings circulated, one question began to echo through Soviet engineering bureaus: If an American tank could withstand their most advanced penetrators, what did that imply for the T-80s' survivability against NATO guns? The answer would soon arrive, not from test ranges but from the battlefield. The first true shock came not from a direct confrontation between superpowers, but from a war the Soviets had expected to validate their assumptions. When Operation Desert Storm erupted in 1991, Soviet advisors quietly anticipated that American tanks would reveal their weaknesses under real combat conditions. Many believed the harsh desert would expose the turbine engine's fuel demands, the electronics fragility, or the armor's supposed limitations against modern long-rod penetrators. Instead, the battlefield delivered a result that undermined the entire predictive framework used by Soviet armor design bureaus. U.S. Army documentation, satellite imagery, and after-action reports showed Abrams tanks not only absorbing impacts that should have penetrated, but in several cases remaining mobile and continuing to return fire with perfect stability. On the rare occasions when Iraqi T-72s, export-downgraded models far inferior to the T-80, managed to fire accurately, their rounds left visible scorch marks and shallow craters on Abrams' frontal armor, yet failed to breach the crew compartment. The thermal images released afterward showed Abrams tanks advancing through smoke, sand, and depleted visibility conditions as if nothing had struck them. For Soviet engineers, the implications were immediate and alarming. If a weakened export T-72 firing older ammunition could not penetrate the Abrams, then the calculus shifted dramatically. What would happen if a T-80U, equipped with its 1,200 horsepower gas turbine, advanced composite turret, and newer gun-launched rounds, encountered these same American tanks? The answer depended entirely on the Abrams' classified armor composition. But the battlefield had provided an undeniable clue. The Americans had achieved something the Soviets had never prioritized: true multi-hit crew survivability. Where Soviet design philosophy had long balanced firepower, mobility, and cost efficiency, U.S. philosophy had elevated survivability to a non-negotiable requirement. Blowout ammunition panels, reinforced crew capsules, and complex armor geometries were not afterthoughts. They were central features. Combat footage of Abrams tanks surviving catastrophic ammunition cook-offs only deepened Soviet concern, because such an event in a T-72, T-64, or even T-80 typically resulted in turret separation and crew loss. Most unsettling of all were U.S. test range results quietly shared among NATO partners showing that the Abrams could withstand impacts from penetrators comparable in velocity and mass to Soviet 125mm rounds. The Soviets now had to confront the possibility that their foundational assumption, that no tank could reliably survive a modern APF-SDS hit, was no longer universally true. This realization forced Soviet engineers to reconsider something even more uncomfortable: whether the T-80, their most advanced and expensive tank, possessed vulnerabilities they had underestimated. As Soviet engineers reassessed their assumptions, the focus inevitably shifted toward the T-80 itself, the machine they had long regarded as the pinnacle of their armored forces. The T-80U represented decades of iterative evolution: a powerful 125mm gun, advanced composite armor, explosive reactive armor, and a gas turbine engine that, on paper, placed it in the same elite class as the Abrams. But as intelligence from the Gulf War circulated, each of these strengths began to look increasingly fragile when compared against the Abrams' real-world performance. The first concern centered on ammunition stowage. While the T-80 used an autoloader that allowed for a smaller turret silhouette, it also placed propellant charges vertically around the crew, an arrangement optimized for rate of fire, not survivability. The Abrams, by contrast, isolated its ammunition behind armored bulkheads with blowout panels that vented explosions upward, away from the crew. In Desert Storm, Abrams tanks took catastrophic internal hits from secondary explosions yet remained intact. The same kind of event in a T-80 would almost certainly eject the turret. Another point of comparison was thermal imaging. American thermal sights, refined through years of investment in night fighting capability, offered ranges that even Soviet specialists had underestimated. U.S. tank crews identified, tracked, and engaged targets before Iraqi gunners could even acquire them. Soviet planners had assumed that battles would unfold at closer ranges where the T-80's speed and fire control could impose parity. Yet the Gulf War demonstrated that the side with superior thermal vision effectively dictated the engagement envelope. And in that environment, the T-80's advantages mattered far less than expected. Armor composition posed the most troubling question. Soviet engineers had confidence in their composite arrays and Contact 5 reactive armor, which was designed to disrupt long-rod penetrators. But Western reports suggested that Chobham-based armor did not merely absorb the kinetic energy of incoming rounds. It redistributed it across non-metallic layers in ways that defied conventional modeling. If even a downgraded Iraqi APF-SDS round failed to penetrate the Abrams, what would happen when a T-80 fired its most advanced ammunition at a production-standard U.S. tank? No Soviet bureau could answer with certainty. By late 1991, internal assessments acknowledged a possibility once considered unthinkable, that the T-80, despite its power, might not defeat the Abrams in a frontal duel. And this uncertainty forced Soviet engineers to confront a larger, more strategic question. How had the Americans achieved an armor system that rendered the expected equations of lethality unreliable? That answer would emerge only when analysts turned their attention to the deeper technological philosophy behind the Abrams. When Soviet analysts finally began dissecting the Abrams' underlying design philosophy, the contrast with their own approach became unmistakable. For decades, Soviet armored development had been governed by strict industrial realities. Designs had to be economical, producible at scale, and capable of operating with minimally trained conscripts. The T-80 represented the apex within that framework. A fast, hard-hitting tank optimized for breakthrough operations in Europe. But the Abrams came from a completely different lineage, one rooted in engineering freedom, high manufacturing precision, and an almost uncompromising focus on crew preservation. Central to this divergence was the armor itself. While the Soviets used composites reinforced with ceramics and layered steel, Abrams' armor incorporated advanced non-metallic matrices whose exact composition remained classified but was widely understood to include ceramic, elastic, and energy-dispersing materials arranged in a way that no Soviet production line could replicate. Instead of relying on explosive reactive armor to defeat penetrators, the Americans designed an internal armor matrix that absorbed, fractured, and scattered kinetic energy before it reached the crew. Test data eventually shared among NATO partners suggested that this armor could withstand impacts approaching the energy levels of modern long-rod penetrators fired from 125mm guns. Equally transformative was the survivability architecture. Blowout panels, armored turret bulkheads, and fuel tank placement were not add-ons. They were integral elements. In Soviet design thinking, the tank was a battlefield asset. Crew replacement was an expected logistical reality. In American doctrine, the crew was the primary asset, and the tank existed to protect them. This distinction, seemingly philosophical, had enormous technical consequences. It drove innovations that allowed the Abrams to remain operational even after sustaining hits that would destroy a Soviet-designed vehicle outright. The fire control system further widened the divide. American stabilization, thermal imaging, and ballistic computation created an environment in which the Abrams could consistently fire with precision at ranges where Soviet analytical models predicted only marginal hit probability. The result was simple but devastating. U.S. crews often fired first, hit first, and survived even when struck in return. For Soviet engineers, this combination of survivability, optical superiority, and energy-resistant armor presented an uncomfortable realization. The T-80 was not a flawed machine. Rather, it was the product of a development path fundamentally different from the one the Americans had taken, and one that, in direct confrontation, might no longer hold the advantage. This led to a final, unavoidable question. In a real, modern battlefield engagement, could the T-80's firepower achieve the results its designers had always assumed? The answer would emerge only through controlled testing and intelligence analysis that followed. As Soviet analysts conducted their final evaluations, they were forced to confront new data emerging from intelligence sharing channels and classified range experiments. In several controlled tests, some conducted by Warsaw Pact partners using captured Western armor plates, others through theoretical modeling, the conclusion was consistent. Even when struck by high-velocity penetrators comparable to those fired from the T-80's 125mm gun, the Abrams composite arrays demonstrated a level of multi-hit resistance that did not align with the assumptions used in Soviet lethality tables. The armor behaved in ways Soviet engineers had not accounted for, dispersing energy through complex internal structures, fracturing penetrators, and preventing spall from entering the crew compartment. This didn't mean the Abrams was invulnerable, no tank was. What it meant, however, was more strategically significant. The equations that had guided Soviet tank design for decades were no longer universally reliable. A modern APF-SDS round could strike an Abrams frontally, leave a crater that appeared catastrophic, and yet fail to disable the vehicle or kill its crew. In Soviet doctrine, such a result was never part of the design requirement. In American doctrine, it was the baseline expectation. The implications for the T-80 were profound. If the Abrams could survive direct hits from rounds of similar performance to its own, then the decisive first-shot kill, the foundation of Soviet armored strategy, could no longer be assumed. The T-80's speed, firepower, and autoloader efficiency mattered far less if the enemy could absorb the initial blow and retaliate with precision at extended range. By the time the Soviet Union dissolved, a quiet consensus had formed within its remaining armor design circles. The Americans had fundamentally changed the nature of tank survivability. The Abrams was not simply a heavily armored vehicle. It was a system engineered around the idea that the crew must live even when the numbers said they should not. And for Soviet engineers who had trusted those numbers for decades, that was the most unsettling discovery of all.